Hello again. I'm going to talk about Hooke's law and simple harmonic motion. It's also called simple harmonic oscillation. You've seen Hooke's law before. Suppose I have a spring here, the spring constant K. So K is the spring constant in newtons per meter. So it's a measure of how stiff the spring is. So if the spring is really stiff and hard to stretch, that's a large number. If it's really easy to stretch, that's a small number. So if I can pull this spring, then if I pull to the right, the spring is going to pull back to the left. If I push to the left, the spring is going to push to the right. And the further I stretch it, the harder the spring pulls back. The more I compress it, the harder the spring pushes back. That gives us something called Hooke's law, where the force is minus Kx, where the more I stretch the spring, the bigger the force. That's like in exercise equipment, where maybe you're trying to stretch some exercise equipment, and the more you stretch it, the harder it is to stretch it anymore. So the force is proportional to how far you stretch it. To stretch it a little bit, it's not so bad, but to stretch it a lot takes a really big force. The minus sign is just telling you the direction. If I pull to the right, it pulls to the left. If I push to the left, it pushes to the right. This is Hooke's law. It says the restoring force, by restoring it means trying to restore this situation to zero, to equilibrium. The restoring force is proportional to displacement from equilibrium. So it's not really a law of nature. There are many systems that approximately behave that way. Molecular vibrations approximately behave that way. Vibrations of beams in buildings. There are certainly a mass on a spring does this. So there are many systems that approximately behave this way. So it's a really important law, we say, but it's really an approximation most of the time. Now, suppose I take this spring and I attach a mass to it. And I stretch it. Notice I attach the mass. Earlier in the semester, I've done cases where I compressed the spring, released it, and launched the mass. I'm not doing that now. I'm attaching the mass. It's connected. Now I pull the mass to some maximum displacement I'll call A. A is the amplitude. That's maximum displacement from equilibrium. I could just as easily have compressed it by the same amount, but so I stretch it here, so I've now stretched the spring. You have to imagine the spring stretched now. Still attached, and if I release this mass, it would now oscillate back and forth like this. That oscillation is called simple harmonic motion or simple harmonic oscillation. So simple harmonic motion is the sinusoidal motion of a mass or system, I'm just going to say a mass at the moment, of a mass subjected to a Hooke's law restoring force. Sinusoidal motion of a mass subjected to a Hooke's law restoring force. Why is it sinusoidal, you say? I'm glad you asked. Let me show you. suppose I hang the mass from the ceiling now, and this is x equals 0, and I push the mass up through some amplitude A and let it go. It's now going to oscillate up and down like this. Now let's further imagine I make a graph of this motion as a function of time. So this is now x, this is time, and as this mass oscillates up and down, I graph it. So if I push it up at time t equals 0, I release it, and as time passes, I graph where the mass is. This graph will turn out to be a sine or a cosine. That's why that's called sinusoidal motion, or even harmonic motion. In mathematics, things that obey sines or cosines are called harmonic. So this behavior is sinusoidal. In fact, if we wanted to write an equation for this, we would discover that x is its maximum, a, times cosine of 2 pi times something called the frequency times the time. What is that frequency? Well, the time for one complete oscillation is called the period. Give it the symbol t. It's time for one complete oscillation. So for the mass to go from here all the way down and all the way back up. From here all the way down, all the way back up. That time is called the period. The number of oscillations per second is called the frequency. I'll show you the units. Period t, it's a time, so it's units of seconds. These are just reciprocals of each other. The period t and the frequency f are just reciprocals. T is 1 over f, f is 1 over t. That is, if it takes, if these are going up and down at 100 times a second, then it's taking 100th of a second to go up and down once. If it takes a half a second to go up and down once, then they're going up and down 2 times a second. So if you think that through, you'll see these are always reciprocals of each other. So t is 1 over f, f is 1 over t, t has units of seconds, so this has units of 1 over seconds, or seconds to the minus 1, but we express it as a quantity called hertz, H-E-R-T-Z, by definition is 1 over seconds. So frequency is expressed in units of hertz, but that just means 1 over seconds. So this equation, which I have not derived, is just says that this curve, this behavior can be written as the amplitude times cosine 2 pi times the frequency times the time. That is pretty readily derived from a comparison between simple harmonic motion and circular motion, which you can find in your book or online somewhere. This quantity 2 pi f, because of the relationship to circular motion and because of just a lot of convenience in mathematics, it just makes a lot of mathematics just tidier, especially in higher mathematics. It's just defined to be something called the angular frequency, omega. So we can also write this as a cosine omega t. And there's a bit of a unit subtlety here. When we're talking about, notice these have the same units essentially, because 2 pi has no units. Radians, but remember radians a meter per meter, so it has no units. This has units of hertz. This has units of 1 over seconds. even though a hertz is 1/2. So just by convention, if a quantity is expressed in hertz, we assume people mean frequency. If it's expressed in seconds to the -1, we assume they mean angular frequency, just by convention. All right, so this is describing that simple harmonic motion that we were talking about. All right, your book then goes on to derive what this frequency and period depend on. And I think it's pretty easy to see that they should depend on how the mass and the stiffness of the spring. As you put more mass here, it takes longer for this to go up and down. As you can imagine, if this gets heavier and heavier and heavier, this would get really sluggish, hard to go up and down. So expect that as this gets more massive, the frequency, the period gets longer. It takes a long time. Excuse me. As the spring gets stiffer, it's easier for the spring to pull the mass up and down, and the period gets shorter. Mathematically, this is actually hard to derive, but mathematically what you get is the period turns out to be 2 pi times the square root of m/k. So that captures this idea that bigger mass takes longer, bigger k takes less time, but where the square root comes from is not obvious, and for the moment we'll just have to accept it. Since frequency and periods are reciprocals, we can also get frequency is 1/2 pi square root of k over m, and you might see it introduced that way. Those are just reciprocals, but you might find it easier to think this way, or you might find it easier to think this way. So all of these equations are very simple, very straightforward. So I suppose I could do a couple of examples. Suppose I have a K of 25 newtons per meter, and I put on it a mass of 2 kilograms. I could ask, for example, what is the maximum force and what is the maximum acceleration? What is the frequency? That's not frequency, that's period. What is the period and what is the frequency? F max. Well, F is minus Kx, so F max depends on how far I stretch it. So I didn't give enough information. I have to decide how far I stretch it. So I've got some spring like this, and I've got to decide I stretch it. Let's say a good amount would be, that's about 10 centimeters. Let's say I stretch it 10 centimeters. So F is minus Kx. So this says if A is 10, F max is then Ka. Notice I left out the minus sign because that's just telling me the direction, not how big the force is. So this is 25 newtons per meter times 0.1 meter is 2.5 newtons. A max. Haven't really mentioned A. Where does acceleration come in? Well, I now know F max, and I know F equals ma. So A max will be F max over m. So 2.5 newtons over 2 kilograms. So that's 1.25 meters per second squared. The period, if I stretch this out by 10 centimeters and release it, is 2 pi square root of m over k is 2 pi square root of 2 kilograms over 25 newtons per meter. Okay, I can't do that in my head. So 2, that's 1.78 seconds. Frequency is 1 over the period, is 0.563 hertz. Angular frequency, if I'd asked for it, omega would be 2 pi times the frequency, would be 3.54 seconds to the minus 1. Be careful of your units. Even though this again is 1 over seconds, we say hertz. Here we say seconds to the minus 1. All right, there you have it. Pretty straightforward. Surprisingly important. Shows up a lot. I'll see you soon.